I'm Aditya Bhatt from Purdue, and today we're going to talk about OptRand, which is optimistically responsive, reconfigurable distributed randomness. This is a joint work with Nivesh Shrestha, Aniket Kate, and Karthik Naik. And so we all know what random beacons are, right? They just generate random numbers at every interval. And they have a lot of applications, as for example, in sharding, in consensus protocols, in e-voting, anonymous communications, so many applications. And so two of the key properties of random beacons are they should be bias resistant and they should be unpredictable. So in a summary, the distribution of random beacons should be identical to a uniform distribution. So nobody should be able to influence them. At the same time, nobody should be able to distinguish between a uniform distribution and a random beacons distribution. So we want to work on Byzantine fault-tolerant random beacons. So we have some T Byzantine nodes who will act arbitrarily and do random things. So one of the things they could do is the worst-case scenarios. Additionally, we also want to have some more ideal properties, which is we want optimal resilience. So we want to tolerate the maximum number of faults that theoretically is possible in that model, which is up to half for us. We are assuming synchrony. And we want to have ideally low communication complexity. We want to have low computational overheads. So by computational overheads, we don't want to use proof of work or VDFs, which are like very expensive mechanisms. And we want to have low latency so that if you want to produce beacons much faster, you have the capability, you have the option to do so. And we also want reconfiguration friendliness. So if a node joins or leaves the system, you don't want to stop the entire protocol and rerun a maybe mega expensive setup protocol just to change one node. So we'd ideally like an efficient reconfiguration protocol. And we look at the landscape of the prior work, and they all seem to have problems in one aspect or the other. So, and the natural research question that we ask as PhD students is, can we design something which ticks all the boxes? And our answer is yes. So we present OptRand, which satisfies all the requirements: resilience, optimal communication complexity, the good unpredictability, and it's reconfigurable. So we present our protocol called OptRand, which is obviously a random beacon, which means it's unpredictable and bias resistant, but it also has optimal resilience, so it can tolerate minority corruption, and it has always quadratic communication complexity, and it also has good latency requirement. So if some optimistic conditions hold, which will be explained by Nivesh, but when these conditions hold, you will actually proceed at network speed. So you will not need to wait for this worst case delay. And if this doesn't hold, then you'll still be proceeding at a fixed rate of 11 capital delta. Here, capital delta is your assumption on the message delivery. So you assume that a message will be delivered within capital delta. And of course, we have a reconfiguration protocol that allows you to, within T+1 rounds, the beacon will still keep producing the beacon values, but within T+1 rounds, you'll have a new set of parties. So I'll try to give an overview of our technique here. So again, we have a system of n nodes, up to a minority of which could be Byzantine faults. And what they'll do is, in every round or every epoch of the beacon, they're going to generate random values, and they'll create what is known as a homomorphic PVSS. So PVSS is a publicly verifiable secret sharing. So what do all of these mean? It's publicly verifiable. So anybody looking at the PVSS share, a PVSS string, knows that there is a number that is being produced by some person, in this case, all these 5 people. And it's also a secret share at the same time. So the value inside, nobody knows until enough people send their shares and they try to reconstruct the value. So this is a PVSS mechanism. And what we'll do is, in every epoch, we'll just pick a leader who could be Byzantine or he could be honest. We don't know. We don't care. So, and we'll send these PVSS shares, and since they are homomorphic, and they'll all generate random numbers and put it inside the PVSS. So they're trying to send random numbers as PVSS to this leader. And this leader is going to combine all of them together. And how many he'll combine is T+1. Because if T of them are from Byzantine faults, then at least one input is truly random. So when you add a random number to a constant, it will be random. So once you aggregate T+1 PVSS, you know that inside this PVSS, the PVR, we'll call this as a PVRS, you know that there's a random number inside. And what we'll do eventually is feed this into an SMR protocol. Because we need to ensure agreement, right? We need to know which PVRS are we going to agree on, because a Byzantine leader could propose multiple PVRS. So we feed this into an SMR protocol to bring agreement. And our SMR protocol guarantees the low latency, the good communication complexity. It also handles the cases where this leader is Byzantine and is not proposing any value. But a requirement of this SMR is that whatever you're inputting into the SMR every round as a leader, it should not cross linear size. Then the communication, all the nice guarantees of communication complexity will go away. So we have this one constraint. So now let's try to see how we can use existing techniques to get to this point. Like how do we construct a PVRS which is of linear size. So I'll try to go over whenever I get some cooperation. Okay, so this is what a general PVSS, when I say PVSS, this is what it looks like. So basically it contains encryptions. So for all the parties involved in the system, so there will be an encryption, and there will be a polynomial which is of degree t. So that you need t evaluations to get to the original value that's inside this that is being secret shared, and there's a proof. And what this proof does is it tells that everybody's encryptions are indeed the right evaluations of this polynomial, and it also tells that the polynomial is of degree t, because if it's more than that, any subset of t plus 1 will, when interpolated, will result in different values. So you need to ensure that the degree is indeed t, and this proof guarantees that. And some facts is that these encryptions are constant sized. So there are n constant sized encryptions here. And the commitments and the proofs are usually linear sized. So the entire string is linear. But the encryptions are homomorphic, the commitments are homomorphic, but these proofs don't combine homomorphically. There's a problem here. So they don't let you aggregate them. So now if we try to take t plus 1 PVSS and try to combine them, you're stuck. Now you'll have a O of nt sized string. So you cannot compress them further. So we have a problem here, and we want to generate a PVRS, right? We want to prove that there's a random number inside and that it's we can input it to the SMR. So we need a linear size string. So what can we do? So it turns out that there is a PVSS scheme by Scrape from the Scrape paper where the proof is removed and they just use a pairing based PVSS. So this the proofs are checked by just doing some pairing operations. Now there is no proof. We can do it, but that's mechanism. There is an algorithm to check, and that's using pairings. And with this, now you can combine, but there is another problem, right? Because it's homomorphic and it can be freely combined, an adversary is combining t plus 1, so it can take t minus 1 honest Byzantine inputs where it knows the value. It can take an honest person's PVSS and generate another negative share of that, so that when you add all of them together, that honest node's inputs gets cancelled and the remaining t minus 1 Byzantine server's inputs are at the end. So now there's a problem. You shouldn't be able to cancel honest node's server. So how can we do that? Turns out there is another simple technique that we can use. And we propose a solution to this called decomposition proofs. Basically what this decomposition proof says is it proves two things. One is that the source of the PVSS, there is a authentication information. So there is a signature of some sort telling that I propose this value. And the second information that's there is a non-interactive zero knowledge proof on what's inside. So now an adversary who's aggregating t plus 1 PVSS does not know what's inside. So it cannot generate shares for a negative of that. So it cannot cancel shares because it doesn't know what's inside. So it cannot generate this decomposition proof. Tying all of these things together, so and recalling our overview, what we're going to do is, again, all the servers are going to send their PVSS shares to this leader who's going to aggregate. Because it's homomorphic, all the PVSS can be combined, but you leave the decomposition proofs as is. But the decomposition proof is constant sized. So now the resulting string is you have a linear sized string, and it's indeed all the checks from the commitment transfer. So you can confirm that it is a degree t polynomial that's being shared. And at the same time, you have proof that these exact 5 people have contributed shares. So at least one of them is honest. So you also have a guarantee that there is a random number inside. So that results in a publicly verifiable random sharing. And so you can take this linear size string and feed it into our SMR, or in this example, I'm just showing it in a bulletin board. And you are getting the guarantees that, all of these people have contributed, it is a correct polynomial, and you get the guarantee that the shares for everybody is correct. And the second, one bonus that we get from this construction Usually you need all the shares to confirm whether the reconstructed value is the value that's inside the PVSS or PVRS. But the nice property that we get from this construction is that once you reconstruct and get the beacon value, you can just give this beacon value and they can guarantee that this is, they can confirm using just the beacon and the PVSS or the PVRS string that it is indeed the right value that's inside. So I don't need to resend all the shares. And this property will take advantage in the SMR part for, which will be explained by Nibesh.
In this work, we make use of built-in fault tolerant statement replication protocol or BFT-SMR to agree on a common set of blocks in the presence of up to T Byzantine failures. So eventually these blocks will contain the PVRS string presented by my friend. So in the context of statement replication protocols, prior SMR protocols, they generally assume threshold setup to achieve good communication complexity. However, the protocols that use threshold setup, they are not reconfiguration friendly. And in the absence of threshold setup, these protocols tend to incur at least cubic communication per decision. This is primarily because without threshold signatures and threshold setup, the size of quorum of signatures or certificate, they tend to be of linear size. So in our prior work, we gave a BFT-SMR protocol with quadratic communication even in the absence of threshold setup. However, this BFT protocol, this BFT-SMR protocol, it has large latency. In particular, it spends 11 big delta time in an epoch. Here, big delta is the non-upper bound delay on the delivery of messages, and because of this, it slows down the protocol. So in this work, we try to optimize the latency or reduce the latency during some optimistic conditions, and using a notion called optimistic responsiveness. So this notion of optimistic responsiveness, it was introduced by Parcel C, and it allows a synchronous protocol to commit responsively at the speed of the actual network delay during certain optimistic conditions. The optimistic condition here is when the leader and 3/4 of the nodes in the system, they behave honestly. We are still tolerating up to 1/2 Byzantine failures. It's just that when certain fraction of Byzantine failures, they start behaving honestly, we get optimistic conditions. The one primary concern with optimistic condition is that we do not know if the optimistic conditions are met or not. So we can't really decide if the protocol should progress responsively or it should just commit synchronously. To get away with that problem with optimistic responsiveness, we have two paths in our protocol. The first part makes progress at the at the actual network speed during optimistic conditions, while the slow path, it makes progress synchronously. And this both fast path and the slow path, they are executing simultaneously. So our final protocol, it makes progress at the speed of the fastest protocol. This slow path, it is actually identical to our repliable BFT. So I will only discuss our fast path. So to progress at the fast path, we have few key challenges. The first challenge is to propagate a linear size message. In our protocol, we have few linear size messages such as proposing a block or propagation of the certificates. The problem is when a Byzantine leader sends these linear size messages only to some honest parties. And if an honest party tries to propagate using some all-to-all communication, it will incur QV communication. The next problem we have is string math cutting. Next problem we have is to change an epoch. When an honest node moves to an higher epoch, we want all honest nodes to move to the higher epoch, right? In a responsive manner. And this is primarily typically obtained in prior works by performing all-to-all multicast of the certificates, which incurs QV communication in our setting. So to propagate large messages, we use two primitives. The first is the linear eraser and error correcting codes or an RS code. Given an N, B RS code, it has two interfaces. The first interface is the encode interface that generates N slices given any B symbols. And the decoder interface decodes the original input from any B valid symbols. And in this work, we set B to be N over N by 4 plus of 1. And the second primitive is the cryptographic accumulators to prove the validity of the slices that we receive. So now let us take a look how we can use these primitives to propagate the linear sized message. For example, we will as an example we will look at the propagation of a block proposal. So to propagate a block, let's say the Byzantine leader signs the block and sends the block proposal to any one of the leaders. So to ensure the block is propagated to all the honest nodes, the honest node upon receiving the block, it will create n slices and create n corresponding proofs. And then it also sends an acknowledgement to all other parties saying that it has received the block. And any honest node upon receiving its slice, it will also multicast the node. And upon receiving 3n by 4 plus of 1 acknowledgement for a common proposal, any node can consider that the block is propagated, and any node can recover the original proposed block with n by 4 plus of 1 slices. So let's try to see why it is safe to consider a block to be propagated when a node receives 3n by 4 plus of 1 x. This is because out of 3n by 4 plus of 1 x, at least n by 4 plus of 1 are sent by honest parties, and these honest parties will send their slice to all other parties. So all other parties will receive at least n by 4 value slices, which is sufficient to reconstruct the original block proposal, since we are using the RS code in n comma n by 4 plus of 1 setting. So we use this same technique to propagate the certificates, although it contains slightly more details. And once the propagation of certificate is done, a node tries to move to a higher epoch. So to move to a higher epoch, we need a synchronization primitive. And in this work, we use the reconstructed secret. We depend on our random beacon protocol, where we reconstruct a secret in every round, and that reconstructed secret we multicast. So the size of that is a constant. So even all-to-all multicast, incurs at most quadratic communication. So using these ideas, these ideas, like we obtain an efficient, optimistically responsive BFT-SMR protocol with quadratic communication and optimistic latency, and it commits a decision in t plus 1 epochs in the worst case. So with this, given our PVRS string and I'll just speed it up. So given our PVRS string and SMR, we get our OptRand beacon protocol as follows. So in each epoch, parties will send a PVS string containing a random value. The leader will aggregate t plus 1 PVRS string to generate a PVRS and input into an SMR. The SMR is will ensure that it will get committed in t plus 1 epochs. And if it doesn't get committed in t plus 1 epochs, the leader will be removed. And in the same epoch, we also reconstruct the secret shared by the leader the last time when it was the leader. And that secret will be used to generate the random beacon. So we also evaluated our protocol, and we find that our protocol performs much better compared to even protocols such as DRAN that generates random beacons every delta time during the optimistic condition. And we find that during the normal condition is equivalent to the state-of-the-art RAN Piper protocol. Yeah. With this, I would like to conclude. Thank you.
So just a quick question on the leader selection algorithm. How do you ensure that an adversary is not chosen? I'm assuming that leader is selected from the group.
Oh, it's any leader election works. Even so round robin works.
And so, what happens if a malicious party is selected as a leader?
So the thing is, if you are a leader, you must have finished the PBRS last time, or you have never become leader. Okay. Within the next time you must have something.